All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So we have a frame here, a compound beam, consists of pin connected members AB and BC. Our frame is externally supported by a roller here at A and a fixed support at C. We're going to try to figure out what's going on at A, our internal pin B, and at C. Before starting this out, I would count up how many unknowns do I have for my entire free body diagram. If we look at that, I would have an AY, I would have CXCY, and my fixed support, a moment here. MC, 4 unknowns. I can't find all of those. I can do this without needing to do my overall free body diagram. So let's not drop. We'll move on. If we looked at just AB, I'll get it drawn on the left here. We would get this free body diagram for AB. We get a horizontal line here. At A, I know I have my roller, so I'll put in an AY. AY. And I also have our 400-pound force. It's going up and to the left at a 60-degree angle. Let's try and make that look like a 60-degree angle. Up and to the left at a, that's still not really 60, but close enough, 60 degrees. Or from horizontal, I could label that as 30 degrees. It's really the same thing. I have over my entire thing from A to B, we know this is 12 feet wide. And as we go up, I have a triangular distributed load, starting at 0 at A and coming up until we get to point B. We know our entire triangle is 300, but it's changing linearly as we go from A up to that max point. At B, I'm not at 300 yet. I'm a little bit below that. So I can't call this 300. I can say this is, let's call it WO though. We'll come in and find WO. Also at point B, I need to get a BY and a BX. So I'm going to guess that goes up for BY and to the right for BX. And just to get everything up and going, let's go ahead and figure out, actually let's go ahead and work with this one right now. I have 3 unknowns on here. BX, BY, AY, I can find all 3 of them. But I need to get WO first. WO I can find using proportional triangles. My ratio of height to base in this big triangle would be 300 is my height, divided by my total width, 12 plus 6, 18, equals my height to base in this little triangle. My height is WO, my base is 12. Basically, we're saying the slope of this line from 0 to WO is the same as the slope of this line. Or if we came in here to our triangle up above, at this point right here, that height is WO as well. It's really all we're tackling here. Our slope's the same. We can relate then. Tangent is all this is. Tangent of this line equals tangent of this one. But I can solve that for WO. My height, 12 feet into this, is going to be 200 pounds per foot. So I know the height of my triangle. Let's come in and apply equilibrium then. 3 equilibrium equations, I can get all 3 of my unknowns. Let's just start by summing forces in the x. Summing our forces in the x direction, I have bx minus my x component of this, I didn't label it, 400-pound force. Should get me to where I need to go. 400 pounds. My angle comes from vertical, so to get the x component, I want to use sine. So minus 400 sine 60 is going to get us to 0. Or solving that one for bx, I'm going to get that bx is equal to 346.41 pounds. We're going to the right. And because this is an internal connection, I want to say on a specific member. This is on AB. And that matters for us because in a second we'll move that to member BC. And I have to change the direction. It'll be equal and opposite as I move from one member to the next. From there, though, I have 2 unknowns in the y, AY and BY. I want to do moments about point, we'll do moments about point A. With positive going counterclockwise, let's sum up my moments about point A. I could also do moments about point B and then some force in the y. Both of these are valid for us. If I sum moments at A, I will have BY causes a counterclockwise rotation, so 12 BY. My 400 and AY pass through A. They won't cause any moment. It's just for my triangle. So I need force times distance in here. This will be a clockwise rotation, so minus force is area for a distributed load, so 1/2 base 12 times my height, WO, 200. Times my distance from the 90-degree corner of this. Let's mark that 90-degree corner here. 1/3 of the way in. If I need to measure that from A, so really I'm saying from A to get to that 90-degree corner, I go in 12 feet. So times 12. And then I come back towards A, so I subtract off 1/3 of my width. Minus 12 thirds is going to get me to 0. If I was summing moments about B, I would be right at that 90-degree corner, and I just say, 1/3 of the way in would be 12 thirds. Where I'm measuring from matters in here. But I can solve this one out for BY. I should get from this that my BY is going to be equal to 800 pounds. We're going straight up. I'm getting a positive from this equation, so I guessed the right direction. Up on member AB. I think I will change that direction around when we move to BC in just a second. With BY known, I could do moments at B, or I could sum forces in the Y. Let's sum forces in the Y. Summing forces in the Y direction. I have AY going up. I have BY going up, so plus 800. And I have my distributed load coming down. Minus 1/2. Our base is 12. The height is WO, 200. And the very last thing I need is my 400-pound force. Its Y component goes up, so I'll add this in. Plus 400 cosine 60 gets us to 0. Which, solving that one for AY, I'm going to get AY is 200 pounds, and it's going up. I get a positive number out from this equation for AY, so I guess the right direction. This is an external reaction. I don't need to say on which member. We only should say that on the internal ones. But that's everything I can get from my first free body diagram. From there, I can just move on and say, well, let's make another one. I could either now draw a free body diagram of the entire beam. That would work for us. BX and BY would get internalized inside of everything. They wouldn't show up on that overall, that global free body diagram. Or I could draw one of just member BC. Either way, it gets me the same final answers on everything. Let's draw one out for BC. So if we come in here, I have just a horizontal line for my beam. We're going from B to C. At B, I have BX and BY. I got the BX went to the right on AB. Equal and opposite tells me we changed that direction. That's the opposite part. But it's still the same value. BX is still 346.41. If we're to the right on AB, then on the next member, we're going to the left. BX is 346.41 to the left on BC. Same idea for BY. It went up on AB. That means we're going down. Equal and opposite. 800. BY is 800. Going straight down here. Along the top of this, I'm going to have a distributed load. We got up to WO in that beginning part. I have some height at the start of point B. I'm not at 0 here. My initial point should be WO, 200. So we'll start here at 200. And it goes over 6 feet until these distributed loads end. So we'll mark a 6-foot distance and say at the end of that point, we've grown until we are 300, our total height right here. 300. And just a linear increase in there. We again have a distributed load. It's 6 more feet, gets us out to C. At C, I can guess directions for everything. I'm going to guess that CY goes straight up. CY. I'm going to guess that CX goes to the right. And I need a moment in here. Fixed supports, resist, moment for everything. I'm going to guess this goes clockwise. Clockwise moment. MC. And we want to work with that. If I have a trapezoid for a distributed load, we want to come and break this into two distributed loads. We can basically say this is a rectangle with a triangle stuck on top of it. And we're going to measure for the triangle. Our distance has to come from the 90-degree corner, so I'll just show where that's at right now too. Let's come in and apply equilibrium into this. I can do any equation in any order to get through this problem. Let's do forces in the x first. Summing my forces in the x direction. I have Cx going to the right and Bx going to the left. Minus 346.41 is going to get us to 0. Or Cx is 346.41. Cx equals 346.41 pounds, and it's going to the right. We should have been able to come in and work with our free body diagram of everything. If we had drawn that out originally, we would have found that from the global free body diagram as well. But we got it here, so it doesn't matter. From there, let's do forces in the y direction. If I sum my forces in the y, cy is my only unknown. This will get me cy going up. I have by coming down, so minus 800. I have two distributed loads coming down, so minus. For the first one, we're 6 wide and 200 tall. That's our rectangle. So base times height, 6 times 200. For the second one, it's our triangle. The bottom of that is already up 200. It's coming down, so we'll subtract it. And it's area, 1/2. Our base is 6. The height should be the difference between the tall side and the small side, because that first 200 went to our rectangle. So times 300 minus 200 equals 0. Cy is my only unknown here. I can solve it for Cy and get that Cy is 2,300 pounds going up. And then finally, our last unknown is MC. I can sum moments about any point I want to get this. Let's do them here at point C. With positive going counterclockwise, summing our moments about C. I have my internal moment, MC. I can say, well, that BY will cause a counterclockwise rotation. So plus, my force is 800, and my distance is 6 plus 6, 12. My rectangular distributed load will cause a counterclockwise rotation. This should be negative MC, because I took it was clockwise. We'll add that in really quick. Negative MC, and then everything else I was saying should make a little bit more sense. Negative MC plus 800 times 12, plus the moment for my rectangular distributed load, plus my force is the area, so 6 times WO is 200, times my distance from C to the middle of that rectangle. Well, I'm going to go 6 to get to the middle, and then half of 6. So times 6 plus 6 over 2. Or my distance here is going to be 9 for this one. And then the next line, we'll do a similar thing for the triangle. It will also cause a counterclockwise rotation. So plus, force is area, 1/2, base is 6. My height is 300 minus 200 times my distance from C to the 90-degree corner is 6. And then I go a little bit farther into this. So I'll add in additional distance a third of the way in. 6 plus 6 over 3, or that one would be 8. This is going to get me to 0 equals 0. If I solve for my couple moment here, MC, the moment that fixed support C resists, works out to be 22,800 pound-feet. I'm getting a positive answer from this equation, so I guess the right direction in my free body diagram, it is clockwise. That would be our final answer for the problem. Hopefully this is a useful video for you. If it was, hit those like and subscribe buttons. Let's watch more videos. Let's help you get an A with JJ.